Good morning, everyone. I'm Rajita. Today we'll be discussing about the fifth experiment in the digital signal processing laboratory. So, our main objective is to find the magnitude spectrum of a signal using fast Fourier transform, and our second objective is to separate the respiratory component from the PPG signal by using the FFT transform. So, so first, what is let us see what is discrete Fourier transform. Like as we have discussed in our last video, it is nothing but the discretization of discrete time Fourier transform. Like the main difference between DFT and DTFT is here we'll be getting our frequency spectrum as discrete frequency sets, unlike which we get in unlike which we get as continuous frequency sets in DFT. So the analysis equation is sigma n equal to 0 to n minus 1 x of n into e power minus j 2 pi by n into kn, where capital N is number of samples that we are taking and the k is at every instant of the signal will be getting our spectrum, and n is small n is the sigma which we are doing for different values 0 to n minus 1. So moving on. So the main thing why we use fast Fourier transform is to reduce the computational complexity. If you take for discrete Fourier transform, the complexity in additions is n square, and in multiplications it is n into n minus 1. But when it comes to FFT, it is only n by 2 into log n for additions and n log n for multiplications. So it is far easier than the than the DFT. So the equation is actually we have to do a bit of derivation, and finally we'll be getting like g of k plus wn into k into h of k. So your wn is nothing but e power minus 2j by 2 pi into k. So this is the equation for the fast Fourier transform. Now let us see how we'll be how we'll be writing the code. Now, so first we have a library called Arduino 50. So that we have to first we have to load that library in our system. Then hash include this is the code for the importing the library, and then Arduino F50 is the name of the library file, and F50 is the name which you are giving it in in this function. So this is syntax for getting the importing the Arduino library, and then we'll be taking 75 samples and we are giving them with these 75 samples, and then constant samples equal to 128. So this we are giving it as this we have to round off the number of samples to the nearest 2 parent, and then initialize it v real, v imaginary, and all to 0, like we are taking two arrays, and then we are extracting the exponent component. So exponent is the name which you are giving in this function, and capital exponent is like which is already defined in it. So FFT dot exponent, and in brackets we have to write number of samples we are taking. So yeah, void, coming to the void setup. This is the baud rate. Serial dot begin 9600, and initialize again in mean and k max value and all to 0. Now for 75 samples 0 to 75, initially we have taken v real and v imaginary as 0. So now we'll be calculating the v real components. So we'll be adding x of I to all the real components and also calculate the mean. Why we are dividing it 128 is anyways we are going to do zero padding for the remaining component. So on a whole we are averaging it to 128, and yeah, for 0 to 128 v real equal to, like after calculating the mean, for removing noise or for normalizing it, we'll remove all the mean we'll remove the mean from the signal. And then this command f50.compute is going to give you the fast Fourier transform in the forward direction. So after computing it, what the values that will be stored in V real and V imaginary are nothing but the your imaginary, real and imaginary components of the output frequency spectrum. So This way we have to give this is for real, this is for imaginary, and this is the number of samples, and exponential we have already extracted it. And F50 underscore forward is nothing but the command which you are going to which we gave it. If in case you want a inverse Fourier transform, just F50 underscore reverse will give you the inverse of it. So if you want the magnitude, F50 dot compute is for calculating the transform, and if you want the magnitude, F50 dot complex to magnitude. Again, we really we imaginary number of samples will give you the magnitude. So, so for 0 to 64, like this is for if you want the uh, actually we want respiration signal. So for we are taking 0 to 64, and we are calculating the max value of it. And yeah, this is for calculating k into 25 by samples into 60. It is nothing but it will give you the pulse rate. So moving back, yeah, this is the F15 Arduino. It will be like this, and the respiratory signal will be like this. Like our respiratory signal is plotted by taking only the first 26 samples. We'll be taking the first 26 samples and then the do moving average and all. After that, for calculating it, we'll be taking the first peak, and this will be the first peak, and using that, we'll be calculating the pulse rate. So the same thing we have plotted in MATLAB also. So our magnitude response is like this, an autocorrelation of PPG signal. So these are mix. Yeah. So the respiration it obtained through Arduino is 21.01 BPM. So that's it with today's experiment. Thank you.